Hello everyone. We are starting a free open lecture in our Discord. All our lectures are held weekly without breaks. If you, viewer, want to ask questions and receive answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the time of the lecture, join our Telegram channel. So, let's move on to what? How will this heap be structured? Well, as I mentioned, it will contain not binary trees, but binomial trees. And for these trees, we will basically define the same heap property. That is, we will have some tree with 8 elements. And we must have the property that a parent's value must be less than or equal to that of the child. This applies to all. Here, a pair of parents and children must be fulfilled. Let's say it's 1, 1. 2, 3, 5, 5, 6, 5. This heap is okay because we performed a swap of the Libra. Well, accordingly, again, if we want to find the maximum instead of the minimum, then we should have more liberty, on the contrary. And this is our binomial tree. What rank did we get? The third rank because we have 3 children here. Then, what other nuance could there be? Some children may not exist. For example, this subtree may not be present. This subtree may also be absent. We can have just this kind of thing. It will still be a tree of rank 3. It's just that there are 2 such pieces of a child here. But it is still a tree of rank 3 because we have a tree of rank 2 located right here. Accordingly, the tree above it must be larger than it. Why can they be empty? Because, for example, how do we place 5 elements? We essentially need to break 5 down into powers of 2. If we convert it to binary, what do we have? 4 plus 1, and this is exactly the 0 order, first order, second order, and we end up with a tree of rank 0. Here it is. There is also a tree of rank 2, and in total, we have a tree of rank 3. That's how it is. So, this is the heap we get. Now, in order to perform these 3 operations, we actually only need to be able to do the merge operation. And for all the others, well, get min, get net. In order to perform push and deletion, we first need to learn how to do the merge operation. Well, let's try to merge 2 heaps. How will this happen? What sizes should we take? Heaps are so interesting. For example, 7 plus 5. Let's say yes, the heap of size 7 will be some unit. This is also a tree of rank 3. A little tree. We have a little tree for now. 1, 2, 3, 4. 5 elements, right? And to make 6, so let's make 5. Here we will have, well, I don't know. This is a tree of rank 3 as well. It turns out, but it kind of lacks this part if you look at it differently. A rank 3 tree, meaning we have this one, but this one is missing, and this part too. Here we have 1, 2, 3, 4, 5, 6. Oh, by the way, these are 6 elements. 7, it will look like this. 1, 2, 3 of some kind. Here we will have a minimum, and the 4th will be with 1. So, now 7 elements, 3 and 4. So, this is a rank 3 tree, and it will have a total of 7 elements.
Want to become a great programmer? Subscribe to our Telegram channel.
So, now let's say I want a tree of rank 5. It will also be rank 3 for me, but with these 2 empty ones, and whatever they will do there, let's say I will have 6, 6, 7, 8. But accordingly, this one will be empty for me, and this one will be empty. The rank 0 tree and the rank 1 tree are empty. Here I also have a rank 3 tree. Let's have a rank 2 tree. 1, 2, 3, 4. How many do I need? 4 elements. I have a path. How am I going to merge this? I see that I have a rank 3 here and a rank 2 there. So, accordingly, I take this tree and try to attach it somewhere here. Definitely. That is, one of his children of the corresponding rank. So I have a rank 0 child, a rank 1 child, and a rank 2 child. Well, I take it and try to hang it here. I already have something here. If there were an empty space, I would hang this here and that's it. But I already have a rank 2 tree here. So what I do is merge these 2. They have the same rank, so how do we merge them? Well, we look at which is smaller, the 2 or the 5. The 2 is smaller, so we will take from this tree and make a rank 3 tree by hanging this here. Now we will have a rank here. So now what we have is that this one is kind of gone, and this one is also gone because we merged them into this one tree. And now we will take this one big tree and hang it right up here. And since it has a rank 3, here we will have a rank 4. But the minimum will basically remain the same. And then we have, accordingly, a rank 2 tree. Here it will be as described. That is, we will have nothing here. If we, for example, later, decide to attach another tree here, let's say a rank 1 tree. So I want a bunch, and I just took something like this, 1 to 2. Very simple. What will I do? I will work exactly with the same tactic. I will try to hang this here. So this rank 1 has, so I'm trying to hang it right here where I have rank 1. There is already something lying here. Accordingly, I take and merge these two trees, rank 2 and rank 3, and this one, rank 1 and rank 2, and I see which is less than 1. It's less than 2. So I take it and temporarily suspend it here. And now I have a tree of rank 2. Accordingly, I will suspend this spot where my tree of rank 2 should be. Here, I have an empty space, and here, accordingly, this will be hanging. Let's say I want to do another merge. Well, let's keep it simple. I want to add another 1 to 2 like this here. What am I doing? I take it and try to suspend it here. I have nothing here, so I just take it and suspend it. In this case, it is necessary to check while suspending that I still have the minimum element here. If it is not the minimum, I will simply take this element and swap it with that one, but I will just take and swap this. The elements are just ones, standing, 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 standing. This merging will be performed for me in logarithmic time of the heap. But it is the binomial heap that serves more as a precursor to the Fibonacci heap. And the Fibonacci heap, it is used in some implementation of Dijkstra's algorithm. For example, in Dijkstra's algorithm, we can significantly optimize its complexity. There will also be a logarithm there, but it will be slightly smaller than usual, slightly smaller. Well, that's what I'm saying. Overall, the binomial heap is used as a precursor to the Fibonacci heap. It's just that the operation, as I describe it, isn't really much better than the regular one, only if you actually have to perform a merge. But at the same time, it's easier to just write the Fibonacci heap right away, which, let's spoil it a bit, leads us to the point where we will have a 1 here, a 1 there, a 1 on the merge, a 1 on the decrease. But here we will have a Lacarit. This is the Fibonacci heap. Let me write the merging function in a way that is clear and detailed so that you can understand it. This is definitely a modification on some kind of merchandise. And we have AB. What will happen here? If A basically pulls, then we essentially return B. If B, then we basically return A. So essentially what happens next? Well, let's say I will always return A. For me to always return A, I need the value in A to be definitely smaller. So if I have B top, I haven't forgotten top. It's like, if my B top is less than A top, then I swap B and A. And then what do we take? We have these children, and they are stored, meaning everything is organized by ranks. And we can actually store them in different data structures that we want. And storing these children is essentially our imitation of rank in the node. Accordingly, we can either use a map here, and if we talk about the advantages, we can sort the map. We can use arrays on the tree, whether they are unordered or in a hash table. We can use any kind of arrays, static or dynamic, it doesn't matter. We can also use lists, even singly linked lists. So, how do we store this? It's just some kind of sequence, whatever you prefer. But for example, I find it easier to write on a map. So, what are we doing here? If we change the stack, then now our main one is now A. Next, we take and suspend. We try to carefully and meticulously suspend B in the children of A. So if we have A, we take and merge the value there, B. From the frame inquisitor, something exists, something lies there. So we take and merge some value, that is, who's morning, from P. rank, but already +1 because there is already something there. We will place it and get just the leg. So we had like K, then we do +K, and here we get a tree of rank K +1, right, in the merge. This is how it would be. Here, from rank K, we take another rank K, and we already get a tree of rank K +1. So we are already at rank +1. What do we put? Merge what? A children of B rank and B, also in the morning from the RAM or something. That is, we are kind of merging the children already. And further, if we have merged a child, then we need to remove a children, remove of some rank, because now it is already in rank +1. Otherwise, that is, if we have nothing there, yes, there is emptiness, like we are putting something here. Imagine we just place it there without merging anything. That is, essentially, we then proceed to set the variable a children from rank equal to b. Now we need to recalculate the rank here. The rank will be the maximum of what we currently have, or b rank +1. We have recalculated this. And that's it. We returned, and here is our merge. This is the merge of two elemental needs defined by keys.
Want to become a great programmer? Subscribe to our Telegram channel.